I'd like to look at an example here of why power series are so important in calculus. So this example is going to make us use this idea here that a power series can be differentiated the same way as any polynomial. So you can take each term of a power series and you can take the derivative just like you would take the derivative of anything else. So this right here, this 1 over 1 minus x, this function, can be represented by this power series. So if you just take, it's a very simple power series, 1 plus x squared plus x cubed plus x to the fourth, and you add up all of these terms on the interval from -1 to 1. And the reason it only works on the interval from -1 to 1 is because this right here is actually a geometric series, right? We get each term by multiplying the term before it by x. So the common ratio here is x. And in a geometric series, it only converges if the common ratio is between -1 and 1. So since the common ratio here is x, that means that x is going to have to be between -1 and 1. But on this interval, the value of 1 over 1 minus x can be represented by this power series. So then what I want you to do is find a power series to represent this. So the first thing I want you to know is this right here, 1 over 1 minus x squared, is the derivative of 1 over 1 minus x. So use this power series to find another power series that represents this function, the derivative of this one. So what we can do here is we can, since we know that this is the derivative, this is the derivative of this, then to find the power series, we can take the derivative of this, term by term. What's the derivative of 1? What's the derivative of x? What's the derivative of x squared? What's the derivative of x cubed? Okay, now I know we don't have the next term here, but can you tell me what the next one's going to be? 4x cubed. And then 5x to the fourth, and then 6x to the fifth, and then so on. And then our general term, if I take the derivative of x to the n using the power rule, I get n times x to the n minus 1, and so on. So this series right here, this power series, is equal to this function. Now notice, and I put this in here, but you might guess this, the interval of convergence for this power series is exactly the same as the interval of convergence for this one. And basically what that means is, if this series converges on this interval, it wouldn't make sense for this series to converge outside of that interval, because it doesn't really have any meaning here. That means that the derivative is not going to have much meaning here. But as long as it converges on this interval for the function itself, it's going to converge for the derivative also. So we can just take the derivative term by term, and anywhere from -1 to 1, if we put any number in for x between -1 and 1, then 1 over 1 minus x squared is going to be equal to this. Now, I want to write this one once real quick with sigma notation. I want you to get in the habit of doing this. We want to write this as an infinite series. So what's the general term going to be? What do I put here? N times x to the n minus 1. And so then the trick is figure out what we're going to start n at. Are we going to start n at 0, at 1, at 7, at what? We could start at 0. Do we need to start at 0? Yeah, actually it would be the same if we start at 0 or if we start at 1. Because if we start at 0, then we get 0 over x. The only thing we might want to be careful about is 0 is on this interval. And if we start at 0, then we get n over x, or we get 0 over x. And if we have 0 over 0, that's indeterminate. We might run into some trouble. So I'm going to keep the 1 there just so we don't run into that trouble. Does that make sense? The gist of this is, if we know a power series for one function, we can take the derivative of that function by taking the derivative of the power series one term at a time.